Hi everyone. Welcome back to Dave's Math channel. I'm your host David Tare, and this is my third video in my series on algebraic number theory. Last time I talked about number fields, which are fields whose elements are algebraic numbers. Today I'm going to talk about a special type of algebraic number called algebraic integers. And as you'll see, algebraic integers have the same kind of relationship to algebraic numbers as ordinary integers do to ordinary numbers. Anyway, let's begin. So first we have to define algebraic integers. And just like algebraic numbers are defined to be roots of arbitrary polynomials with integer coefficients, algebraic integers have a very similar definition. The only difference is that the polynomials have to be what are called monic, which means that their leading term is equal to 1. So here we have a polynomial, general polynomial degree n that's monic, has the form x to the n plus a sub n minus 1, x to the n minus 1, plus a sub n minus 2, x to the n minus 2, so on down to a1, x plus a0, where each of these coefficients, a0, a1, up to a sub n minus 1, those are all integers, arbitrary integers, but the leading coefficient, if you like a sub n, is equal to 1. And remember, for algebraic numbers, it doesn't have to be. Uh, but for algebraic integers, it does. So let me just give you some examples of algebraic integers. So the simplest example is just ordinary integers. And to see that ordinary integers are algebraic integers, just note that if n is an ordinary integer, then it satisfies the linear monic polynomial x minus n. Because x minus n equals 0 means x equals n. Not too exciting. But it is an integer. But notice that if the polynomial was, say, ax minus b, where a isn't necessarily equal to 1, then the root would be b over a. That would be a rational number, but it wouldn't be an integer unless a was plus or minus 1. And, it doesn't help to use minus 1 for the leading term. You can always use plus 1. You can just negate all the other coefficients. So I think you kind of see how that works, at least for the trivial case where you're dealing with ordinary integers or ordinary rational numbers. Anyway, example 2, this is probably the next simplest example. These are what are called quadratic algebraic integers. And it turns out that plus or minus the square root of n, where n is any non-square integer, these things are also algebraic integers. And how can we see that? Well, it's pretty simple because square root of n, and also it's negative, satisfy the monic quadratic polynomial f of x equals x squared minus n. Notice that the term in front of x squared is equal to 1. It's a monic polynomial, monic quadratic polynomial. If we started something like 2x squared minus 3, then you have the square root of 3 halves, and that's not an algebraic integer. It's an algebraic number, but not an algebraic integer. So I think you kind of see how that works. And then another good example is the golden ratio. I'm sure you guys all know about the golden ratio. I have a few videos on it. It's a very famous algebraic number. It's equal to, it's usually given the symbol phi, Greek letter phi, and it's equal to 1 plus the square root of 5 over 2. It's approximately 1.618. I think most of you guys are familiar with this number. And this turns out to be an algebraic integer as well. And how can we see this? Well, it satisfies the monic quadratic polynomial f of x equals x squared minus x minus 1. Phi squared is equal to phi plus 1, which is just another way of saying that phi squared minus phi minus 1 is 0, or f of phi equals 0, where f of x is x squared minus x minus 1. And so this is a quadratic polynomial. It has two roots. So not just as the golden ratio, one of the roots, but it's what is called its conjugate, this other thing, minus phi inverse, or if you like, minus 1 over phi, which is equal to 1 minus the square root of 5 over 2. This is a negative number, but this is the other root of this equation. So this one is also an algebraic integer. And in general, when you have two or more roots of what's called an irreducible, I haven't talked about irreducible polynomials yet. This one turns out to be irreducible. But if you have a irreducible polynomial then its roots are what are called conjugates. So it turns out that minus phi inverse is a conjugate of phi, or if you like to make a conjugate pair. And complex conjugates are example of conjugates, but since this is a real number field, there's no complex conjugates in this field. If it was say f of x was x squared plus 1, then the roots of x squared plus 1 are plus minus I. So our and I and minus I are conjugates, as I'm sure you guys all know. Anyway, and they're complex conjugates as well. But anyway, let's go to the next example. So now let's consider a higher degree. I mean, it could be degree 2, but it's a general degree, k greater than or equal to 2. Um, and n is any number, any integer that's not a perfect kth power. Then it turns out that the kth root of n, did I call this n or m? Yeah, the kth root of n is also an algebraic integer. And that's pretty easy to see too, because it satisfies the monic degree k polynomial x to the k minus n. X to the k minus n equals 0, x to the k equals n, or in other words, x is the kth root of n. That's just one of the roots. There's actually k roots of this polynomial, but one of them is the kth root of n, which is always positive. Anyway, and then as long as k is positive. And then the final example I give here, I think this is kind of an interesting one. These are what are called roots of unity. So imagine we have some, again, imagine k is some arbitrary integer greater than or equal to 2. And now we have another integer which is called j, a non-negative integer. It can go from 0 to k minus 1. And then we have this thing called zeta sub k. This is just a primitive kth root of unity. I'm going to get into what that is. Zeta k is equal to e to the 2 pi I k over 2 pi I over k. And that's equal to cosine of 2 pi over k plus I sine 2 pi over k by Euler's formula. And if you take that to the jth power, so we have zeta k to the jth power. These are just powers of the primitive kth root of unity. These are the form e to the 2 pi I j over k. And that has the form cosine 2 pi j over k plus I sine 2 pi j over k. And I don't really have a picture on this slide, but the pictures look kind of nice. If you looked at where these are complex numbers, obviously they're imaginary. Most of them are imaginary, and they all lie on the unit circle, and they're all equally. They're like they form a regular k-gon. That's what's interesting about them. They form a regular k-gon with one of the vertices along the positive x-axis. X equals 1 is one of the vertices, and then these other numbers are the other k minus 1 vertices of this regular polygon, and they satisfy the polynomial x to the f of x equals x to the k minus 1. That's why they're called kth roots of unity, because x to the k equals 1, so you could say x is a kth root of 1, and it turns out they're actually k kth roots of 1. When you were learning algebra in high school, you probably learned that if k is even, there's only there's two kth roots of 1, namely plus or minus 1. And there's only one kth root of unity if k is odd. Well, we're talking about real roots, but there's k complex roots in general. By the fundamental theorem of algebra, every degree k polynomial always has exactly k roots, complex roots, possibly with multiplicities, but in this case there's no multiple roots, so there's k distinct roots of this polynomial. And like I said, a picture's worth 1,000 words. Here's a picture, and this isn't quite the same example I gave. This is an example of the fifth roots of 7. So just like there's 5 fifth roots of 1, or in general there's k kth roots of 1. It turns out there's k kth roots of n, where n is any positive integer. It's not a perfect kth power. In this case, 7 is not a perfect fifth power. So there are 5 fifth roots of 7. And here they are. Here's what they look like. And they all have this form. I mean, it's the same form I showed you before. Actually, there's 5 of them. They only wrote down 1 here. They wrote down the primitive 1. So the primitive one is just the one where you go counterclockwise 72 degrees from the positive x-axis. That would be the one pointing, pointing like that. I can't really do it with my hand, but the one in the first quadrant. Um, that's pointing almost vertically up, but it's still in the first quadrant. That is the root that they're writing down here. But then there's four others. You got cube root of 7 times cosine of 4 pi over 5 plus I sine 4 pi over 5. And then you have the same thing with cosine 6 pi over 5 plus I sine 6 pi over 5. Or you also have the same thing with cosine 8 pi over 5 plus I sine 8 pi over 5. Or you could go all the way up to 10 pi over 5, but that would just give you cube root of 7 because the cosine of 10 pi over 5, that's just 2 pi. And that's the same as the cosine of 0, which is 1. And the other one would be the just 0, cosine of 2 pi is 0. So those are the five fifth roots of 7. Kind of nice, I think. And they're all algebraic integers, and they're all conjugates because they all satisfy the same degree 5 polynomial. And last thing I want to talk about today, I know this is a pretty technical talk. Maybe I could have left this slide out. I don't know. But one reason we care about algebraic integers is that they form what's called a ring. And I haven't talked about rings yet. A ring is almost like a field. The only difference between a ring and a field is that you can't, in general, divide. You can't take reciprocals, or you can't, in general, divide elements of a ring by other elements of a ring. They're not closed with respect to division. Uh, it's like the integers. The same thing with the integers. If you try to divide 3 by 4, you get a fraction, 3/4. So the integers you can't divide by, but you can do everything else with them. You can add, subtract, and multiply. And they're closed with respect to all three of those operations. And they also have additive inverses, just not multiplicative inverses. So a ring of integers, imagine we're starting with an algebraic number field. I talked about those in my last video. So an algebraic number field is just a field whose elements are all algebraic numbers. And then you can talk about the ring of integers of that number field. And those are just the set of algebra. It's a subset of elements of K, your number field, that are algebraic integers. That's all that is. It's a ring. It turns out these things are rings. And I'm just going to list some examples here. So these are kind of like the previous examples I went over. The ring of integers of the rational numbers, which we denote as Q, the field of rational numbers, is the ring Z of ordinary integers. So that's a ring. Q is a field and Z is a ring. And this is the smallest, it's kind of the trivial example of a ring of integers. Every other ring of integers contains the ordinary integers, but it usually contains a lot more stuff too. So let's just look at a few more examples. How about let's let n be a square-free, and in case you don't know what a square-free number is, a square-free number is just a number that isn't divisible by the squares of any integers. All the powers, if you write its prime factorization, its prime factorization involves primes all raised to the first power, no power greater than 2. So 30 is an example of a square-free number because 30 is 2 times 3 times 5, but 24 isn't because 24 is 2 cubed times 3. It has a power greater than 1. So anyway, as long as n is a square-free integer that's congruent to 2 or 3 modulo 4, that means that the remainder when you divide by 4 is either 2 or 3, not equal to 1. If it was equal to 0, it wouldn't be square-free. It would be divisible by 4. But there's only 3 possibilities if n is square-free. It can either be 1, 2, or 3 modulo 4. But if it's not congruent to 1 modulo 4, for instance, 5 isn't. 5 is congruent to 1 modulo 4, so we're not doing 5, but we could do 2 or 3, or 6 or 7. You get the idea. So anyway, if n is of that form, then it turns out that you can look at the algebraic number field Q joint square root of n. And it turns out the ring of integers of this number field is what we call Z, and we use a bracket here instead of a parentheses. We write Z a bracket square root of n. That's just all numbers of the form a plus b times the square root of n, where a and b are ordinary integers. So for instance, 3 plus 5 if n was 6, we could have 3 plus 5 times the square root of 6, 2 minus 4 times the square root of 6, 8 minus 55 times the square root of 6. You could just substitute any integers for a and b, but you can't substitute rational numbers. So, for instance, 3 plus 5 halves times the square root of 6 isn't an algebraic integer. Or 6 plus 7 times the square root of 6 divided by 5. That's not an algebraic integer either because you're dividing both a and b by 5. So you get the idea. And then, so that's kind of nice. But then things get a little weird. If n is congruent to 1 modulo 4, it turns out the ring of integers isn't really what you expect anymore. It's not z of square root of n this time. It's z of 1 plus square root of n over 2. And this should, I mean, think about n equals 5. That's probably the simplest non-trivial example of this. 1 plus square root of 5 over 2. You should recognize that. That's the golden ratio. So the golden ratio is actually, I mentioned that was an algebraic integer. Well, it turns out it belongs to the algebraic number field q adjoins square root of 5. So even though it's not of the form a plus b times square root of 5, it's still an algebraic integer. So if n is congruent to 1 mod 4, you get more stuff than you might think. If you like, there's two different ways you can write this set. You can either write as a plus b times the algebraic number 1 plus square root of n over 2, where a and b are once again ordinary integers, or you can write as the form c plus d times the square root of n all over 2, where now c and d are odd integers. Those are two different ways you can write this. They're equivalent. It's not too hard to show that. But that's what the ring of integers looks like if n is congruent to 1 mod 4. It has a little bit different form. And then the last example I'm going to give you is the ring of integers of, this is a specific example, the ring of integers of q adjoin cube root of 2. This is the set z adjoin cube root of 2, which is really just a set of algebraic integers of the form a plus b times the cube root of 2 plus c times the cube root of 4. You have to get the cube root of 4 as well as the cube root of 2 because remember, rings are closed with respect to multiplication. So once you have cube root of 2 in there, you have to have the cube root of 4. Anyway, that's what that one is. So that's really all I'm going to talk about today. I know a lot of these, the problem with studying algebraic number theory is that it is kind of abstract. You have to know a lot of abstract algebra. That's kind of the tool of algebraic number theory. That's why we have to do things like, rings and fields, because that's the way we study algebraic numbers or algebraic integers. And you might wonder why we're studying these complex sets and concepts. Well, it turns out that these things are going to shed a lot of light on ordinary integers. So just kind of bear with me. We're going to learn a lot of fun facts. We're going to learn how to solve a lot of really interesting Diophantine equations. I think I mentioned some of those in the first video I made. For instance, we can find all solutions to all primitive Pythagorean triples, or all Pythagorean triples. I'll probably do that next time. That's a fun example. And that involves ordinary integers. And you'll see how algebraic numbers and algebraic integers play a role in that. So even though we're learning a lot of very abstract stuff right now, you'll see how we can kind of bring it home to more concrete stuff, more stuff we're familiar with. Anyway, that concludes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time. Bye.